guys, welcome back. This time we're going to talk about making a star. So how would you make a star? Think about it. What kind of elements do we have out there in our universe that we're going to make those stars out of? Well, hopefully you tell me we got a lot of hydrogen, some helium, and a tiny little bit of everything else is left. And that's basically what the star is made out of. So if we start talking about stellar formation, what we're really talking about, what happens when we go out there and we birth those stars. So guys, let's talk about stellar formation. Now, I want you to realize that when we talk about a star, that star's lifetime is a continual composition between gravitational collapse, and that collapse is always going to be inward because it's gravity, and then we have this gas pressure that's radiating outward, and so remember it's going to push outward and it's going to cause the expansion. If you think about what we talked about with our sun's core, okay, that core was radiating energy outward, radiating then that pressure of those gases that is expanded outward. Well, hydrostatic equilibrium occurs when those two conditions are equal and opposite. And we, again, talked about that relative to our sun. Remember that because this is gravitational collapse, that collapse is going to cause that star to decrease in size. And when I say that star, we're really talking about what's going on within the core itself. And then the rest of the star kind of responds to what's going on within the core. Now, when that core starts collapsing, then you're going to talk about gravitational collapse, and so therefore you're going to talk about potential energy being converted into kinetic energy, and that star then is going to start heating up because that energy is given off. Expansion, on the other hand, is going to cause that star to cool down, and so you have the energy given off, expands, cools everything. We're going to keep coming back to this, guys, and you're going to think, okay, she said it enough, she doesn't need to say anymore. But really, that's really what's describing what's going on within that star and what happens as we start talking about those evolutionary sequences as that star then goes through its lifetime. The biggest factor, though, in terms of determining not only the sequence, but how that star forms, how long it takes that star to form, how long that star is going to be from the time that it's a little protostar to where it finishes, is going to be its mass. Now, we're making the assumption that the only place that this mass comes is from the star itself. If you've got a star that's in a binary system, and so you have mass from one star that's being pulled off by the other star, and that other star then is changing its mass because the addition of what's going on, or the subtraction of that mass because of the fact that its mass is being pulled off, then all bets are off. But as long as we just look at the mass that the star had to start with, then that is going to be the biggest factor in determining what's going on within that star all the way through. So we've got to talk about where stars are forming, and they form from material called an interstellar medium. Okay? And that's mostly hydrogen, and guys, you should have expected that because most of everything out there is hydrogen. This will be both neutral and ionized, so that means we've taken and we've stripped off the outer electrons. Or in some cases, we stripped up all of them, and so you just have electrons that are roaming around and the nuclei of what's left. So we have mostly hydrogen, about a fourth of that's helium, and then you have these dust particles that are around there. And we think that those dust particles are probably surrounded by frozen water. And then within that dust, you have all this other stuff. And that can include carbon, it can include nitrogen, water, all those kinds of things that are going to make up the dust. Now remember, guys, what I said about our sun. Our sun is a third-generation star. So every time you have a star that forms, then goes through its evolutionary sequence and blows up, okay, you're putting more of all those heavier elements out there. So we think that during those first generation of stars that form, they probably just had mostly hydrogen and helium. But as you have these stars that go ahead and go through their evolutionary sequence and blow themselves apart and in the process form these heavier elements, then those heavier elements get dispersed throughout the clouds, the interstellar medium, if you want to talk about it. And so you have more and more and more of those heavier elements. But even though I say more and more, guys, we're still only talking about less than 2% of the material within that cloud is going to be anything other than hydrogen and helium. But keep in mind, guys, that other stuff is basically where we're from. Now, if we think about where stars usually form, they form in these really big, giant, clumpy molecular clouds. And yes, guys, I want you to underline that word molecular. They are typically 50 to 200 light years across. Remember, a light year is simply the distance that light travels in a year. Remember that our solar system is very, very small, much less than a light year. Okay? Very cold, we're talking about 10 K, so we're talking about close to temperatures that are absolute zero. And, when you think about these clouds, you think about what you see in the sky. And so you think of clouds as having a little bit more of a density than what you see in the air. But realize, guys, these are dense only by virtue of the fact that they're sitting next to basically a vacuum. And so we're only talking about 10 to maybe 1,000 atoms per centimeter cubed. So we are really talking about essentially right above what's considered a vacuum. And yeah, they're very, very large. They're very cold, which means they're going to tend to stay together. And because they are very cold, they can then go ahead and form molecules as opposed to just atoms or, ions where you've had your electrons that have been stripped off and you just have free electrons and then your nucleus is there. So kind of think about these big, huge, kind of dark clouds in there. And that's what's going to make a star. But now, certain things have to happen before that star is going to go ahead and form. And we know that these stars, which by the way, guys, are called protostars, form within those clouds when, remember I said they were clumpy, so that means part of that cloud is more dense than other parts of the cloud. And where you get those clumps, they're the densest part of the cloud, and they can become unstable. And when they become unstable, they go ahead and start moving and doing some things like that, and they start contracting under the influence of their own gravity. They've certainly got mass, and you remember from when we talked about Newton's law of universal gravity, that every piece of mass out there is attracted to every other piece of mass out there. And the closer those pieces of mass are, the more the gravitational attraction. And so something starts them to go ahead and move, and they become unstable, and they start getting close to each other, and as they get close to each other, gravity takes over and pulls them together. But as I said, something's got to cause that instability within the cloud to go ahead and start the initial collapse. Something has to serve for a trigger, because they just can't start doing that on their own, because they're out there, it's really cold, they're not moving very much. Something has to go ahead and start them to really become unstable or to start moving. And so we think there are several triggers that are going to go ahead and cause that to happen. One of them is self-gravity. Just the fact that you have one piece of matter, they're not moving very fast because it's only 10 K out there, but they are moving. And this piece of matter runs into that piece of matter. And so you can, just by random motion, go ahead and start that instability and start that motion toward each other. And then it just kind of feeds in on itself, and you can build up your star that way. You also have what's called radiation pressure from nearby stars. So you've got these stars that are radiating energy, and that energy is radiated out in all different directions. And so some of that radiation gets into your cloud. It starts heating that cloud up. Those particles are going to start moving faster because they're hotter. That can go ahead and cause these molecules or to run into each other, and so you can start building it that way. And that then kind of alludes to those collisions. Something starts that cloud moving where you have collisions. Collisions can go ahead and produce then that motion that's going to cause that clump to go ahead and grow. Then we've also got shock waves or compression waves. We know that those stars that are out there certainly have gone through their evolutionary sequence, and we're going to find out that when those stars do that, if their stars are the right size, those kinds of things, they're going to go off and they're going to form novas or supernovas with these phenomenal explosions. And so that shock wave gets sent out, and that shock wave then can run into the cloud and go ahead and start it compressing. So there's a number of ways that instability can go ahead and get started, or the motion within that cloud gets started, and you start having then those clumps growing larger, and ultimately that's what's going to form your star. So this pre or protostar then is basically what you have in the process of forming a star, and that's going to form deep within the molecular cloud. Now the problem is that molecular cloud is really cold, and so it's really not going to be shining with its own light in the visible part of the spectrum. And so that cloud is basically opaque to visible light, but it's not opaque to infrared. And the next session we'll do main sequence line, and then after that I'm going to put the last three, or these three sections together, and we're going to look at stars. And I'm going to show you this cloud that has these very, very, very deep red objects in it, little bitty tiny red dots. And that's a picture that we're going to look at in infrared, and these little protostars are going to show up as really hot little items. Okay? So that's how we can at least see what's going on. Not that we can actually see that protostar yet, because remember that protostar is forming deep within that cloud, and that cloud is opaque to visible light. And so we can't somehow take that apart and go down into it. So we've got to use whatever mechanism we can come up with to be able to see those stars, and it happens to be infrared light. Now, the other thing I want you to know is that the larger the mass of the protostar, then the shorter the time it's going to take for it to contract. Obviously, guys, think about it. The larger the mass, then the more gravitational attraction you're going to have, and so you can pull that material together even faster than what you have if your mass of that protostar is not very great. Well, if you think about our sun, it took about 30 million years to go ahead and form. Now, that's an extremely small percentage of its actual lifetime. Okay? Extremely small percentage. Because remember, guys, our sun is about 5 billion years old, and we think it's going to go on for another 5 billion. Again, I've rounded that off. So think about a billion years relative to a million years. Million is 10 to the 6th, billion is 10 to the 9th. So very small percentage. But it does take a little bit of time. And so when we talk about these really large stars, we're down to under a million years. And for astronomical times, that's essentially the blink of an eye. So now, remember we've got this material out there. You've got this cloud. You've got these clumps within these clouds that are starting to contract. And here in just a minute, we're going to see there's also rotating. But those clumps are going to have to shrink quite a bit. Now remember we had 10 to about 1,000 atoms per centimeter cubed. Well, we've got to increase that density a huge amount. And you can see there by about 10 to the 20th times if we're really going to start making that star shine by its own light. So you've definitely got some collapsing you need to do in there. And as that cloud collapses, what's going to become that star. Now, I need to stop here for just a minute, guys. And when I talk about the cloud collapsing, realize you generally have these really big molecular clouds, and a lot of times you will form more than one star in there. So it's not the entire star that is collapsing to go ahead and form one star. It's that section within those clouds where your clumps grow that are going to start collapsing and form then those stars. And so we're going to talk about open clusters and globular clusters, and how they all probably formed right around the same time from the same material. And that gives us then a chance, because of this cloud, we assume that it's essentially the same all the way throughout. We can look then at these stars, and if the only thing that is different in terms of their mass, we know they formed essentially at the same time out of essentially the same material, then it gives us a feel for how these stars change relative to their mass. So, like I said, I may talk about the cloud collapsing, guys, but I'm really talking about the clumps within the clouds that are eventually going to go ahead and form the individual stars. Now, think about what you learned in your 5th grade science class. You talked about something called potential energy and something called kinetic energy. Potential energy you probably talked about as stored energy, whereas kinetic energy is energy of motion. Well, we're going to come back to those same ideas here. When those particles start falling inward because they're collapsing because gravity is pulling them inward, then you're going to take potential energy and you're going to convert that into kinetic energy. Potential energy because the material is far away from the center, so therefore it has a higher potential. So therefore, as I go from a higher potential energy and that material falls in toward the center, then that's at a lower potential energy. Remember, guys, that idea of matter and energy can neither be created nor destroyed. You can only change forms. Okay, so we're going from a potential energy, which is stored energy, into a kinetic energy. And that kinetic energy is energy of motion, but we also know that kinetic energy, if we talk about the temperature of the molecules, then temperature really is is a measure of the average amount of kinetic energy of the particle. So basically, guys, if I go ahead and increase my kinetic energy, I'm causing the particles to heat up. And generally, if they heat up, then they're going to tend to radiate energy out. So that's what's really causing those clumps to go ahead and heat up. It's the fact that that potential energy has been converted into kinetic energy as the particles fall inward. And like I said a little bit earlier, that energy is radiated in the infrared part of the spectrum. So infrared is longer wavelengths than visible light, a little bit lower in energy, a little bit lower in frequency, but we can still see it with an infrared camera. And so I've said there kinetic energy is seen as heat, since temperature is a measure of the average amount of kinetic energy of the particles. Now, as the temperature increases, which you're going to expect it to do because you've got more of these particles falling inward, then so does the average motion of the particle, since the average motion of the particle is related to the temperature of the particle. Now, guys, these particles are moving, and these particles, guys, are just atoms, and depending on whether they've had their electrons stripped away yet or not, just these atomic or subatomic particles later on. And so they're going to be moving in random motion, and they're going to run into each other. Well, as they run into each other, that will also cause a change in the energy, and those molecules then are going to be breaking apart because of one molecule running into another molecule, or the fact that you've got enough energy around there to go ahead and pull off those electrons or to break those bonds that are holding the molecules apart. That are holding the molecules together. So when you break those bonds, those molecules then come apart and go back into their individual atoms. And then, got enough energy, you're going to start pulling the electrons off of those atoms to go ahead and form ions. Or eventually, when we get to what's going on like our sun, you literally have enough energy in there to pull all of the electrons off. And so there you just have negative electrons and positive atomic nuclei that are roaming around. And we're going to have to get to that point before we actually have a star formed. And remember, we're looking at what's going on within the core, and then everything else around that core, which is a star, then responds to what's going on within the core. And so here, remember I said that as that protostar collapses, you have motion, circular motion in there. Well, that goes back to the idea of conservation of angular momentum, or just conservation of momentum. And you can think of momentum as mass in motion. And I've put the example down here, which let's talk about the example first before we go back and talk about what's going on with that star. If you're very good at guessing what my drawings are, that's actually a person on ice skates. Can't you see those ice skates down there? And so you've got an ice skater, and I know all of you have seen this happen before. That ice skater goes ahead and starts turning, and they've got their arms out really wide. Okay? Well, now think about what those arms are relative to their axis of rotation. So you can think their axis of rotation is simply right down the middle of their body, and they've got their arms out, which means I've got that mass far out from the center of my axis of rotation. And then you know as they start bringing their arms in, and a lot of times they will bring them in and up so they cross them over their head. Well, I have decreased then where that mass is relative to my axis of rotation. And as I do that, if my axis of rotation, if that mass is coming in closer, then to keep everything the same conservation numbers, then your speed has to go up. So if I decrease my mass and bring it in closer to the axis of rotation, then I speed up. And that's basically what's going on with the conservation of angular momentum. And so with what's going on with that collapsing protostar, as I have more and more mass, and that mass gets pulled closer into its rotational axis, then that protostar is going to speed up. It's going to start rotating faster, just like what this person on roller skates is starting to do. Well, that becomes very important because then that is going to speed up. That's going to have all kinds of effects later on as that star is forming, what's going on within the micro clumps that are around there, which ultimately are going to become the planets. The other thing that's going to happen, I want you to think about a pizza dough. You've got somebody that you've seen going ahead and they've got the dough, and they go ahead and they flip that dough up and they start spinning it. Well, the other thing that's going to do too is going to flatten out. So we'll ultimately get to that idea too, that as they start speeding up, that's going to cause that whole cloud to flatten out, and then that's when we're going to form basically our little solar system, because of the sun being at the center and those other clumps being outward. But we've got a ways to go before we get to that point. Okay? So right now, I just want you to know is that mass of that protostar increases and the radius is decreasing because everything gets pulled in closer, then that whole rotating protostar is going to be rotating faster. Now, at some point as that protostar continues to form and the core continues to collapse and the rest of the star tends to be sitting there right on the core itself, we're going to have that star giving off particles in a continuous outside flow or outward flow. And those are called the solar winds. And we alluded to those and certainly talked about those relative to the sun. But we also find solar winds are formed at the beginning too. And in terms of why, we're going to come back and look at that a little bit more when we talk about stars and evolving stars off the main sequence line and what's really going on at that point as it settles down. But you can kind of have some instability within there, and everything then, as it's being pulled together, you have these stellar winds that start coming off, and they're coming off at speeds approaching 500,000 miles an hour. I mean, 450,000 miles an hour. And I want you to remember that number as we talk then, not next time, but the time after. And I'm going to show you a star that's in the process of forming, and you're going to see that it has jets going out both above and below that follow right along on the axis of rotation. Well, guys, we're also going to talk, too, later on when we talk about these stars, is what's going on within the magnetic fields. And those magnetic fields also contribute to the fact that you have winds that are coming up both above and below. This is called bipolar flow, and we see it in something called a T Tauri star. And a T Tauri star is a star that's just getting ready to settle down and become a normal star, which we haven't talked about yet. So what is a normal star? A normal star is simply a star that is converting hydrogen into helium. Now, our little protostar hasn't been able to do that yet because the core isn't hot enough to go ahead and start doing that. But we're certainly getting close to that point. And that's one of the indications that you're getting close to that point. It's when you start seeing these winds that are coming out that are ejected both above and below. We'll also see that bipolar flow not only in stars, we'll see it in galaxies as we have material given off that way. So we will see this bipolar flow later on when we talk about galaxies. Now, these winds, when they come off, these solar winds, are incredibly energetic. And so what's going to happen is you still have all this gas that's kind of left over from the initial clump that's forming into our star. And so because these are so energetic, then it's going to cause these nearby gases from other protostars as well as material from the original star really to be blown away. And you're going to have holes, and you're going to have columns and all kinds of things. And I'm going to show you these pictures here, not next session, but the next one. And you can see that, it just literally looks like something blew that center portion away. And so those then, when you have these T Tauri winds that go out and blow this other material away, that's another way of starting more stellar evolution, more condensation there, of looking at new stars forming because then of the internal outward flow of those winds. So they can basically go ahead and start the whole cycle all the way over again. And a lot of times that's exactly what you see. You'll see almost a continual formation of stars because of the fact that these T Tauri winds go on, and especially if you've got a lot of material out there, they're going to go ahead and start that compression all over again. And so you'll have one star formed after another. Now, as I've kind of said earlier, these protostars may also be forming planets, and so I have the major clump, the one in the middle, that goes ahead and forms a star. But we also have these other clumps that are around there, and those clumps then will form the planets. Now, these T Tauri winds, these winds can certainly be deadly. Thinking about what we talked about with Mercury, remember that Mercury, we feel like, had a crust and part of a mantle that was simply blown off by these solar winds. Was it blown off by the solar winds? Was it blown off by collisions? That's certainly going to change the behavior of what's going on within those planets. The other thing it's going to change is, you still have that material, that smaller clumps that didn't quite make it into a planet or things like that are still roaming around the early parts of the solar system as it forms. And so the solar system that you see right now within these protostars is certainly different than what ultimately you will see. Now, let's go back to thinking about what's going on within our little protostar. It's still collapsing because you are still adding gravity. You're still adding mass, which is tending with gravity to pull that mass in closer and closer and closer. And so as I pull that core in closer and closer and closer, remember we're going from potential energy into kinetic energy, so that core is heating up. At some point, given enough compression, I'm going to go ahead and reach the temperatures and the densities necessary in that core to go ahead and start those thermonuclear reactions. And that's really what makes a star a star. The protostar is not shining under light produced through thermonuclear reactions. It's shining under light produced by heat. Now, as soon as I get that core to where I can start producing thermonuclear reactions, where I can start taking hydrogen and smashing it into another hydrogen and forming helium, I now have a star. Okay? So a star is born, guys. Like I said, that protostar has become a star because it's collapsed enough to reach those really high temperatures and densities required. So as we talked with what was going on with the sun, you know that energy is released. Think about that proton-proton chain. And that's what's happening in the core of this star now, is that nice proton-proton chain is going on. So you've seen this statement before, guys. A star shines by emitting its own energy, certainly what our sun is doing. That energy is produced from those thermonuclear reactions within the interior of the star, meaning within the core. And then the rest of the star tends to respond based on what's going on within the core. And so a star is nothing more than an enormous ball of extremely hot gases shining under its own power. Once that star is settled down, once that protostar is settled down into a star, it's going to be on that main sequence line. Remember the HR diagram? And as we've talked, it's going to stay there about 90% of its lifetime. And then we're going to look at the evolution of these stars, and that evolution is just the process by which that star is going to go a sequence of radical changes during the rest of its lifetime as it moves off the main sequence line. And once it moves off the main sequence line, guys, it's no longer converting hydrogen into helium. So once that star is a star, I want you to know the star shines by emitting its own energy, and that energy is produced from those thermonuclear reactions when inside the interior or the core of the star. So basically, guys, a star is an enormous ball of extremely hot gases shining under its own power. And so with that, we'll go ahead and talk about the main sequence next time. See what happens. See you then.